Right, so we're going to look at resonance structures, and then that will give us some information on how benzene, when it has certain substitutes, directs electrophiles to certain areas of the benzene ring. So let's just look at resonance for a minute. So we're used to the Kekulé structure of benzene, which looks like that. However, there's no reason why I couldn't have drawn it with just my double bonds there, and there. And these two different structures are called resonance structures of each other, and you can use curly arrows to show how one converts to the other. The double bonds just move like so, to give you a new structure, and then to go back they would just go like so. And we know that neither of these two is the reality, and that's why we draw benzene with a circle in the middle. And that's the one that we actually use because we know it's neither this structure or this structure, but somewhere in the middle with all 6 p orbitals overlapping to form a delocalized structure. So the reason we have to use resonance structures is because we're trying to represent molecules as little pictures, which of course they're not. But this is just a failure of our model by drawing them in this way or this way. Neither is actually correct, it's this way, which is the better representation of it. Okay, so let's look at some other resonance structures. Okay, so here we have a carbonyl group showing the carbon-oxygen double bond. However, you could have drawn this with this being a single bond with a minus charge on the oxygen and a plus charge on the carbon. And again, these would be resonance structures of each other. We actually know that the C double bond O bond is polarized, with this carbon being delta positive and this carbon being delta negative. So it's somewhere in the middle, but both these two structures here and here represent two extremes of that structure. So when we looked at phenol chemistry, we noticed that if you have your benzene ring like so and your oxygen attached, then on your oxygen is a p orbital with a pair of electrons, and that pair of electrons can be partially delocalized into the benzene ring like so. Remember, these are all overlapping like so. So that increases the electron density of the benzene ring. And we said that's the reason why phenol is more reactive than benzene. However, when we reacted phenol with bromine, we noticed that the bromine adds in the 2, 4, and 6 position. So here's phenol, and when I reacted it with bromine, we formed 2, 4, 6 tribromophenol. So why did the bromine add in those positions? Why didn't it add in this carbon and this carbon? And we're going to use this idea of resonance to try and explain that. Okay, so here's phenol, and I put the lone pair of electrons on the oxygen atom, and that's how we've drawn it so far. Okay, so what we could do is we could draw this in a slightly different way, in that these two electrons could come down like so and form a double bond there. However, that would mean that carbon forms 5 bonds, which of course it can't. So in that case, this double bond would have to move, and those 2 electrons would go onto that carbon there. So we would be drawing phenol in a slightly different way, where we would have a double bond there, but now there would be a positive charge on the oxygen atom. There would now be a negative charge on that carbon, and those 2 double bonds have not been affected. But again, there's another way that we could draw this, in that this pair of electrons could come down and form a double bond there, which would mean this pair of electrons would have to break to go onto that carbon there. So if we draw out the result of those electrons moving around, the top hasn't changed, but now I've got a double bond there, a negative there, and that double bond has stayed the same like so. So again, that is another resonance structure. But surprise, surprise, there's another one I can do. This pair of electrons can come down there to form that double bond there, but this double bond would have to break and become, those two electrons have to sit on that carbon there, which would mean I end up with negative charge there, double bond there, and again the top remaining the same. And then the final would be that goes there, and I end up to my original structure. Now, no, the actual reality is somewhere in the middle of those four structures, but hopefully you can see that when you take the average of those resonance structures, you can see the electron density has appeared on the second carbon, the fourth carbon, and the sixth carbon there. So if your electrophiles coming in to attack and for the bromination of phenol, that's going to be Br+, Br+ is going to be attracted to the second carbon, the fourth carbon, and the sixth carbon more than the third and the fifth carbon because they haven't got such a greater amount of electron density. So let's look at a group now which is actually electron withdrawing from the benzene ring. An example of that would be nitrobenzene. So that arrow there just shows that it is actually a dative covalent bond. So don't worry too much about that bit there. Okay, so what can happen is that these electrons from the nitrogen-oxygen bond can pop onto the oxygen, which means this double bond can pop out to form a double bond with the nitrogen there. So what would be the result of that? Well, obviously these two double bonds haven't been affected, but I've now got a double bond there. That is now O minus. That dative covalent bond hasn't been affected, but now I've got a positive charge on that carbon like so. Okay, so let's just move those electrons over there and just see what is the result of that. So again, the nitro group has not been affected. However, now I've got a positive charge on carbon number 4. And then finally, those electrons can go down there. So I now have the positive charge on carbon number 6. So if you are an electrophile coming in who is attracted to electrons, funnily enough, where would you rather go? Well, you're not going to be particularly attracted to that carbon, and that carbon, because if you're an electrophile and you love electrons, you are going to avoid the positive carbons. Instead, you are going to go to these two carbons here, which haven't had that more positive charge build up on them. So that's why, first of all, nitrobenzene, the ring is deactivated because the electrons are being withdrawn. But when you do get an electrophile onto it, they will go into the 3 and the 5 positions.